Thanks. As Nate said, I'm going to talk about Lagrangians SR3 instanton and Atiyah-Floer conjecture. This is my pleasure to give a talk here. I should start the talk with a disclaimer that this is going to be based on, the talk is going to be based on a paper which is still being written. So if you like, it's going to be, I'm going to talk about a few theorems that we claim that we can prove, but I'll try to just talk about the main ideas in the proof of at least the main theorem. Hopefully that will compensate for that issue. Okay, I should also say that this is also based on a joint work with Kenji, Fukaya, and Lipyanskyi. This is a symplectic geometry talk. Let me firstly tell you what symplectic manifolds I am interested in. Fixed Riemann surface sigma G, and we're gonna punctuate once, and we look at the loop which goes around the puncture once. Associated to this, we can define a character variety, an SU2 character variety, which is the space of representations of the fundamental group of this punctured surface to SU2. And we require that this representation maps the loop around the puncture to the element negative identity in SU2. And of course, there is an action of the Lie group SU2 on this space by conjugation, and we look at the quotient space. So for example, we can be a little bit more specific by picking a presentation for our fundamental group. Let's pick the standard presentation given by the loops that are during the case that genus is equal to 2. In general, this character variety can be identified with the space of 2G tuples of elements of SU2, which are supposed to satisfy this one relation. And then again, we are modeled by the conjugation action of SU2. So SU2 acts on all of these guys, A1 up to BG by conjugation. This is a nice space. This is in fact a smooth manifold. You can see that it's dimension 6G minus 6. It's not hard to see where this dimension is coming from. So the degree of freedom to each of these matrices in SU2 is 3, the dimension of SU2. So overall we have 6G from here. There's one relation in SU2, so we would subtract by 3. And then there is another SU2, which we should subtract by another 3. In fact, more than this is true. So we will see that this is a symplectic manifold, like it's a smooth fauna variety. Okay, so let me firstly describe the tangent spaces to this symplectic, to this manifold, and then I will explain what the symplectic structure is. So the Lie group SU2 acts on its Lie algebra by the adjoint action. So if we have some representation of the fundamental group of our Riemann surface, we can associate to it the vector bundle corresponding to this action, which I'm going to call it add of alpha. So this, because alpha is flat, this is a vector bundle coming with a flat connection. And what we can say is that, okay, all right, good. So what we can see is that the tangent space to this character variety at H, at the connection alpha, at the representation alpha is given by the first homology with coefficient in this flat vector bundle of rank 3. Good. So now we can define some symplectic form on this space where, if you look at two, this is an unfortunate choice of notation. Probably it's better to use maybe, instead of, we're looking at the tangent space at some alpha, and here maybe zeta 1 and zeta 2, we're trying to look at the omega of two such forms. And for that, we remember that these are elements of H1. We look at the wedge product of those guys and integrate over sigma. So there's a matrix part, which we also kill that part by taking trace. So this is the standard symplectic structure on this space. Okay, so let's look at some special cases of this character, right? In the case that the genus is equal to 0, this is going to be the emptiest space. It's not hard to see. In fact, in the case that genus is 1, it's also a very simple space. It's just a point. So the first interesting case would be that this guy has, we'll look at the genus 2 case. So in this case, the character variety is going to be a complete intersection. So it's symplectomorphic to the intersection of 2 quadrics inside the 5-dimensional projective space. In particular, so you can see that, like, for example, you can take just a standard quadric and another one, sigma lambda I is the I square, where lambda i's are distinct. Okay, so it might sound a little bit, I guess, there's a more natural choice of a character variety where we don't puncture and we look at just representations of the group. So the description in terms of the presentation of the fundamental group is going to be the same thing as before, except that here instead of negative identity, we put negative identity. So this is just going to be exactly the space of representations into the space SU2 without puncturing our surface. The advantage of the character variety that we've been working up to this point is that that one is a smooth manifold, but this one turns out to be a singular manifold. And this singular manifold is related to the original version of the Atiyah-Floer conjecture. So if people are interested, I can just tell a little bit about this in the discussion part of the talk, how, I'm going to talk about some variation of the Atiyah-Floer conjecture, how it's supposed to be related to the original version, and, what some proposals about how, this guy can be defined in the case that we use this chi even of sigma. But for the rest of this talk, I'm not going to look at this space. As I said, this is a singular space, and things would be much more complicated in that case. Good. Okay, so up to this point, we had the symplectic manifold, and we look at a bunch of examples. Now I want to explain one natural way that you can construct Lagrangians inside this symplectic manifold. Take a 3-manifold M. So these Lagrangians are coming from 3 manifolds. Our symplectic manifold was defined in terms of surface, and now we're going to use 3 manifolds to define Lagrangians. Take a 3-manifold M, and we're going to require that the boundary of M to be our surface sigma g, and we also have to add another connected component in the boundary because of the next condition that I'm going to require. I'm going to require a path which goes to base on the puncture inside sigma g to a puncture inside T2. So now we again can define some character variety, space of representations of the fundamental group of not quite M, the complement of this path omega in M into SU2 again. And similar to the case of the surface, if we take a loop which goes around this omega once, we're going to require that the elements in our character variety maps this loop omega to negative identity. And again, like as in the case of the surface case, we're going to divide by the conjugation action SU2. So you can immediately get a map into the character variety of a genus G-Riemann surface by taking a representation and restrict it to the boundary sigma g. And I should also say that the dependence on omega is not very essential. In fact, it only depends on omega as a 2. It only depends, this character variety depends only on mod 2 homology class of this path omega. And because of, because of that, and also partly because of having a simpler notation, I'm going to drop that from my notation. From now on, I'm going to call such a space as chi of M. So there's a theorem of Herald which says that any such, so now we have a space chi of M which a priori might not be even a manifold, but it has a restriction map to chi of sigma G. And there's a theorem of Herald which tells you that this guy can be perturbed into an immersed Lagrangian of the symplectic manifold that we started with. To be more precise, Herald's theorem is about the case of the even character variety that I mentioned briefly in my last slide, but his proof can be adapted to this case. In fact, in this case, it's even easier because you don't have to be worried about singularities. And, we want to do, Floer homology with this Lagrangian, so it's good to know that, something about the behavior of this Lagrangians in terms of, if they are unobstructed or not. In fact, we can see that, at least in the case that, okay, so we start with such guy, and then Herald's theorem tells us that we can perturb it into an immersed Lagrangian. If this immersed Lagrangian turns out to be embedded Lagrangian, then it is a monotone Lagrangian with minimal Maslow number 4. Some remark about Herald's theorem that, the choice of perturbation in Herald's theorem is not canonical. You might want to use different choices of perturbations, but something which is true is that if you pick 2 different perturbations, then the symplectic manifolds that you would get, the Lagrangians that you would get are Lagrangian cobordant to each other. In fact, something is slightly better is correct. I don't want to make that very precise here, but let me just talk about some mention one manifestation of this better property. That in the case that this, let's say that you start with some 3 manifold and you can define this chi of M without any perturbation. Then this Lagrangian is, this smooth Lagrangian that you obtain is in fact some canonical Lagrangian inside our symplectic manifold. We usually, maybe sometimes, when we work with Lagrangian Floer homology, for example, we care about Lagrangians only up to Hamiltonian isotopy. But these guys are Lagrangians which are defined as a canonical subset, and they're not just defined up to Hamiltonian isotopy. Okay, are there any questions up to this point?
Yeah, I had a question. This is Nate.
Go ahead.
Your theorem about if this is embedded, then it's monotone with minimal Maslow 4. Is there any statement along those lines if it's not embedded, if it's immersed?
It is expected to be that you can still get some monotone as some, you have to add some bounding cochain to your immersed manifold, which is coming from gauge theory. Once you add such a bounding cochain, it is expected that you would get some unobstructed pair of the an immersed Lagrangian without choice of a bounding cochain. But it's it's not a theorem at this point. It's just an expectation. Kenji has some way of some proposal on how to define this choices of bounding cochains, but there are some analytical issues which need to be modified in order to get the analog of this theorem. Okay,
thanks.
No problem. All right, so I'm gonna first, okay, so here we define 3 manifold Lagrangians. I'm gonna first look at some special instances of these Lagrangians, and then I'm gonna talk about some generalization. So if you, ideally we would like to get Lagrangians from manifolds with 1 boundary component. So let's say that you have some 3 manifold with boundary component of 1 less genus, sigma g minus 1, then there's an obvious construction that you can apply to construct a three-manifold with boundary sigma g and T2. What you do is that you take the product of the two-dimensional torus and an interval, and you just take the boundary sum of these two guys along one of the boundary component of this auxiliary three-manifold and your original three-manifold W. So this is what you would get. That I'm going to call this W sharp. Okay, so is there a question in chat, or I don't see chat, so in case
no, I was just sending out your notes again.
Okay, yeah. Okay, good. So once you apply this construction, you would get now, three-manifold with boundary sigma g and T2, and you can apply, the construction of the previous slide to get some, to associate a Lagrangian W, a Lagrangian to W, which I'm going to call this chi-sharp of W, which is the special case of the construction from the previous slide. Maybe I should also be a little bit more specific about the choice of W here. The choice of W in this case is just 1 point times the interval inside I times T2. So it's coming from the auxiliary part, doesn't touch W at all. As a further special case, maybe we can look at the case that W is the handlebody of genus G minus 1, and then we can apply the above construction, and it's easy to see that in this case we would get a Lagrangian which is diffeomorphic into Cartesian products of G minus 1 copies of S3 or SU2. So this is a Lagrangian one genus above, so inside chi of sigma G. For example, in the case that genus is equal to 2, you would get some Lagrangian spheres inside your symplectic manifold of genus of dimension 6. Okay, so again, there's a slight generalization of this construction, which instead of working with manifolds which have boundary sigma G and T2, we look at three manifolds with boundary two different surfaces which don't, neither of them doesn't have to have genus 1. We also take a path between these two guys, and in the exact similar way, we can, in the exact same way, you can define some inverse Lagrangian inside the product of the character variety of sigma G and the character variety of sigma H. Okay, now we want to look at the case of closed three manifolds. We are eventually interested in invariance of closed three manifolds. So we take one such closed three manifolds and fix a Heegaard splitting of this guy, which I'm going to just, for the convenience of notation, I'm going to assume that this guy has, this Heegaard splitting has genus G minus 1, which means that you decompose your three, you find a separating genus G minus 1 surface inside Y such that the complements is the connected components of the complement are handlebodies of genus G minus 1. So in particular, now you can associate to each of these guys H1 and H2 two Lagrangians using the construction that we just talked about, these three manifold Lagrangians. And a theorem which is due to Wehrheim and Woodward, which it says that if you take the Lagrangian floor homology of these two Lagrangians, then this is going to be an invariant of the three manifold, which by that I mean that this Lagrangian floor homology doesn't depend on the choice of your Heegaard splitting. So if you pick another Heegaard splitting, you would get isomorphic three manifolds. I'm going to pick a notation which is a slightly, I guess it's unconventional. I think Katrin and Chris use this notation. I'm going to call this, I'm going to denote it by SI sharp, and I'm going to call it symplectic frame floor homology. Both the notation and terminology are coming from the gauge theory side that I will talk about it in a second. Okay, good. So let's get a sense about this invariant for a little bit. So we want to, I mean, this is Floer homology of two Lagrangians. So the first thing that you would do is that you take the intersection of these two Lagrangians, and those guys are going to be the generators of your Floer chain complex. Okay, so we want to see what are the generators of this theory, if we can get some good topological description for them. So the generators of this Lagrangian Floer homology is going to be the intersection of these two Lagrangians. And remember that to define chi-sharp of H1, what you would do is that you take your handlebody H1, you take the boundary sum of this guy with I times T2. So it's the top part of this picture. And then there is a path which goes between the two boundary components. You would do something similar for H2. So you get chi, you take the connected sum of a boundary sum of H2 with an interval times T2. So that would give you the bottom part of the picture. And there's a natural way that you can glue these two guys. And once you glue these two guys, you would get the three manifold, which is Y connected sum, the three-dimensional torus T3. I'm gonna call this three manifold Y3, Y sharp. And you should also notice that these two arcs and the top and the bottom part of the picture can be glued to each other, and they would, it's just the copy of a point times S1 inside T3. A straightforward application of Van Kampen theorem would show that the intersection of these two character varieties can be identified with the space of representations of the complement of this loop W into SU2, such that if you take a loop, a small loop which goes around W or omega once, it's supposed to go to -1. And then again, as usual, we take the quotient by the conjugation action. Okay, so I wanna get a different description for this intersection. So I'm just gonna I just copied what we got from the last slide, which is a characterization of the intersection point of the two Lagrangians, and I'm gonna call this chi-sharp of Y. It's useful to get a geometrical interpretation of these guys in terms of connections. So we fix a three manifold. We fix an SO3 bundle, rank 3 inner product vector bundle and Y sharp. Any such three bundles and a three manifold is just determined by a second H-T-fold Whitney class, and we just require the second H-T-fold Whitney class of this three manifold to be the Poincare dual of this loop omega. So we can look at the space of all flat connections on this bundle, modular automorphisms of this bundle. And it is just a well-known standard fact that by monodromy, this space can be identified with representations of the fundamental group, in this case, with a chi-sharp of Y. So this is something not special to dimension 3. You have similar facts about in any dimension, but something which is very nice about dimension 3 is that there's a functional with this set as the critical point. So this function is called the Chern-Simons functional. So it's defined on the space of all connections, given any connections on your your bundle of rank 3e. You can define the value, you can define some S1 valued function, which is called the Chern-Simons functional. I can write a very explicit formula. I'm not sure it's going to be helpful, so I'm not going to do that, but it's a very well-known functional, which we're going to use it in a rather formal way for the rest of the talk, so I don't bother to write down the explicit formula for this. But what I want to point out here is that the critical point of this functional, that this is the Chern-Simons functional, not the critical point of our bundle. The critical points of the Chern-Simons functional are exactly the classes are given by the classes of function connections on E, which are flat. So it's exactly the same spaces here. So in particular, it can be identified with chi-sharp of Y. Okay, so we started with some version of Lagrangian floor homology, and the generators of this, the intersection, Lagrangian floor complex of these two Lagrangians can be identified with the critical points of this Chern-Simons functional. So this would suggest some other approach to define a three-manifold invariant. And this is what is called frame floor homology. So this frame floor homology, or I-sharp of Y, is exactly the Morse homology, in the infinite dimensional Morse homology of this functional, which is called the Chern-Simons function. This is, this is, it's probably fair to say that some version of this was defined for floor, and some special case of floor general construction was brought to attention by Kronheimer and Mrowka, because this is supposed to be an analog of some well-known invariant Heegaard floor homology. Because I'm going to assume that maybe other people here are symplectic geometers, not gauge theorists, I just want to point out some fact here, which is some fact about the analysis involved in the definition of I-sharp of Y. On the Lagrangian floor homology side, when we do floor homology, the main geometrical objects for us are going to be holomorphic strips and Lagrangian boundary conditions. So the analog of holomorphic strips in Lagrangian floor homology here would be gradient flow lines of the Chern-Simons functional. And these are given by connections and the product of our three-manifold times arc, which satisfies this instanton equation or anti-self-dual equation. Like the case of Chern-Simons functional, it's not going to be very important for me what exactly this is, but it's just a self-dual. So here we're looking at the curvature of the connection A, and we require that the self-dual part of that to be 0. In particular, this is an equation which can be defined on any Riemannian four manifold. Okay, so at this point we have two different invariants of three manifold. One of them is coming from gauge theory, which is this frame floor homology, and the other one is coming from symplectic topology, which is symplectic frame floor homology. These are both homology of some chain complexes. So the chain complexes in both cases are generated by flat connections on this three-manifold Y-sharp. Remember from the last slide that we identified the critical point of the Chern-Simons functional with chi-sharp of Y. So at least the chain groups are isomorphic to each other, but the differentials are not necessarily the same as each other. And the version of theorem that we prove here is that for any three-manifold Y, these two invariants, these two floor homology theories are in fact isomorphic to each other. In fact, this can be regarded as some version of the Atiyah-Floer conjecture. So the original version of the Atiyah-Floer conjecture is about the relation of some variation of frame floor homology to some other variation of symplectic frame floor homology, which is, even on the symplectic side, it's not completely clear what should be the invariant in the original version of the Atiyah-Floer conjecture. But here, fortunately, there is one candidate, which is symplectic frame floor homology of Wehrheim and Woodward. Okay, I'm gonna maybe explain the strategy of the proof of this theorem, and then spend 2 slides on the main analytical ingredients in the proof. Okay, as we said, there are these two invariants that we want to show they are isomorphic to each other. This one, if you look at, this is the Morse homology of some Chern-Simons and some functional, in this case, the Chern-Simons functional. And like any other version of Morse homology, the value of our functional defines some sort of filtration on this chain complex. So the differential here, I mean, to each critical point here, we associate the value of the Chern-Simons functional, and then the differential decreases this filtration. So an important point here is that it's not quite a fact, but something which is almost correct is that the filtered chain homotopy of this chain complex is also a three-manifold invariant. So this is related to the fact that the Chern-Simons functional is, is a topological functional. It doesn't depend on the choice of a metric or any additional auxiliary structure under three-manifold. And a similar fact holds for the symplectic flame flow homology, that this guy is also filtered, and we can get almost a three-manifold invariant from this filtration. I should say that the filtration here is related to the fact that the Lagrangians are defined canonical. They are not defined just up to Hamiltonian isotopy. Okay, so warning here is that this is not quite correct. You have to make some modifications, because in general you have to make, to both of these two theories, you have to make some perturbations to guarantee transversality. But you can get almost filtrations by picking some perturbations and let the perturbations go to zero. So the strategy to prove the theorem is just to define, of course, you want to show that two invariants are isomorphic to each other. So we're going to define some map from the chain group of the first one to the chain group of symplectic frame floor homology, and it's going to satisfy two properties. The first one is that this is a chain map, so it would induce a map at the level of floor homology groups. And the second property is that this chain map is going to be, so if you look at it, if you decompose it with respect to the filtrations, so the first part is the identity map, so the part which doesn't change the filtration level. Remember that these two guys are naturally identified with each other, so it makes sense to talk about the identity map here. And then there is a part which decreases the filtration. So in particular, because it has this form, it's sort of like a upper or lower triangular matrix, so that the diagonal entries are all equal to 1. So in particular, this is your chain map is an isomorphism, which, by combining these 2 points, you would see that, the induced map at the level of floor homology groups would be also an isomorphism. In fact, you can get more out of this. As I said, these 2 invariants are filtered, and this phi would give you some isomorphisms of filtered chain homotopy type of these complexes. Okay, so but what is the challenge here? So the main challenge here is that on the gauge theory side, you have your invariant is defined by the ASD equation, and on the symplectic side, it's defined by Cauchy-Riemann equation. So your phi, you need to define your chain group phi, you need some mixture of the ASD and the Cauchy-Riemann equation. And this, by ASD equation again, I mean the instanton equation that I mentioned a few slides before. So the analytical ingredient to define this map is introduced by Max Lipyanskyi, which we're going to call it mixed equation. I'm going to define what I mean by mixed equation here. So you fix some close-oriented surface, possibly disconnected. For example, in our application, it's going to be the union of a genus G Riemann surface and T2. And to this guy, we can look at associated character variety, which in our case is going to be exactly chi of sigma G, but it doesn't have to be just, it could be, the 2 connected components could have, for example, different, the general could be more than 1. We look at this region inside the complex line. So we look at the unit disk inside in C. So we have omega plus. It has, I'm going to divide it into two half disk, omega plus and omega minus. And mixed equation is the equation which is defined in these two regions. So the solution of the mixed equation is going to be a pair of connection and omega minus times sigma, and a map from omega plus to this symplectic manifold chi of sigma. Here is for the connection, I have to be a little bit careful with the choice of the second HTFL within class, but it's probably easy to read it out from what I talked about in the previous slide. So it's just going to be something which is coming from the punctures and sigma. U puncture is connected component, and that would induce some omega 2 for it. Okay, and this A and U are supposed to satisfy, so the connection A is supposed to satisfy the ASD equation, and the map U is supposed to satisfy the Cauchy-Riemann equation, so it's a holomorphic map. So up to this point, these are not touching each other. You have some connection and you have some map, which is supposed to be holomorphic, and the connection is supposed to be ASD. But the important condition for these two guys is some compatibility condition along the y-axis here, which is called the matching condition. So for each point on the y-axis on the boundary of omega plus, omega minus, this connection A, if you restrict the connection to that point times sigma, is supposed to be a flat connection on sigma. And furthermore, this is supposed to be the class represented by this connection, the isomorphism class of this flat connection, is supposed to be the same as the value of your map U at the point 0 and y. So this is some sort of the analog of the Lagrangian matching condition in Atiyah-Floer theory. And the main reason that the analysis here works here is because this condition and the boundary is a combination of a Lagrangian matching condition, a Dirichlet, and a Neumann boundary condition. So that's, at its core, that's why this is a good analytical definition. Okay, are there any questions about the definition of mixed equation here? Okay, so if there are no questions, let me just say that the map phi is defined by some global. Okay, so before I talk about the global version of this, I should say that this mixed equation satisfies some nice analytical properties. Some of these things, many of these things were proved previously by Max, like this. So this mixed equation defines some Fredholm problem. There is some compactness property, which is a combination of Gromov and Uhlenbeck compactness. And there's also some regularity property here. Okay, and now to define the map phi, we use some global version of this mixed equation. So there's a four manifold part, which is, in this case, it's going to be cooked up from our Heegaard splitting. So it's going to be handlebodies here, H1 and H1 sharp and H2 sharp coming from our handlebodies. And then, we use them to form this four manifold X. There's also some other part, omega plus, which is some region inside the complex plane. And this phi is defined using a pair of a connection and a map from omega plus, which, I probably, for the sake of time, I'm going to go through that part very quickly, but it's basically the main point is that on this four manifold side, A is supposed to satisfy the ASD equation, and our map U, which is from omega plus into character variety chi of sigma, is supposed to satisfy the holomorphic curve equation. And there are there's a matching condition for the mixed equation that I said in the last slide, and there are some other, like for example, U and eta 1 and eta 2 are supposed to satisfy some Lagrangian boundary conditions, and there are some also asymptotic condition and some condition on the L2 energy. But the key point here is that such moduli spaces are used in the definition of our map phi.
Ali, you have a question from Rohil Prasad. Rohil, you can go ahead and unmute yourself.
Oh, yeah, just a quick question in terms of the construction of X. Should this be thought of as, well, stretching the cylinder Y cross R kind of sideways along the Heegaard surface? Is that how this thing is produced?
Well, you can think about this almost. So you can think about, let me see if I can try to write down here. So this is maybe Y, your 3-manifold, which in this case is really Y sharp times R. And then there's a homomorphic strip part. And then there's a matching line here. So something interesting happens here, which is this changing, from the configuration of connections to the configuration of homomorphic strips. So there is a matching condition where, in this picture, it's good to just, stretch it on both sides. But the picture is essentially something like R times R3 manifold Y. Does that answer your question?
Yeah, I think so. Yeah, thank you.
Okay. Okay. So I want to say something very quickly. Initially, I want to say a little bit more about the closed open string map. But it turns out, okay, when I was writing the slides, I noticed that I was too ambitious. I'm just going to talk about some manifestation of this relation between closed open string map and the mean maps.
Yeah, there's a question from Paolo Ghiggini. Go ahead, Paolo.
Yeah, so I wanted to ask what are the asymptotic conditions when you go vertically to x to plus or minus infinity?
Okay, that's a great question. That's a great question. You don't need any. You wouldn't require any conditions. Somehow, something which is important is that your connections are. I mean, there's a condition on the L2 energy here. So A and U has finite L2 energy, and then you would see that this implies that there's a symplectic once you go in either of these two directions, in some sense it would converge to one of our Lagrangians, but you don't need to specify which, something more than this. So no conditions there. No.
Sorry, I missed a word. You said you get close to what Lagrangian?
So on this end, for example, once you go here, you would converge to some point in eta 1. Okay, so notice that an element of eta 1 can be also thought as a flat connection on this H1 sharp. So on the gauge theory side, it's some element of, sorry, not eta 1. This is not. Right? And our Lagrangians chi sharp of H1. Sorry for the bad handwriting here. But and it would converge to some point here, but you should think about an element here also as a flat connection on our 3 manifold H1 sharp as well. Okay.
Okay, thank you.
No problem. So, okay, so what do I want to say about the closed open string map here? So on the symplectic side, we have, if we have two Lagrangians in a symplectic manifold, then we have an action of the quantum homology and Floer homology of L1 and L2. which is defined by counting holomorphic strips with one interior mark point. So in particular, in this case, we would get an action of the quantum homology of our character variety and symplectic instanton homology of Y. This guy, at least when we work over complex coefficient, has a very nice description. In fact, there's a set of generators for the quantum homology, which are coming from the homology of sigma g. Once you pick some element in homology of sigma g, there's a standard construction that you can apply and get some element of homology of this space, which is called mu of alpha. I don't think these are the original defined by Atiyah, but probably goes back to Mumford, but I think they're also called Atiyah classes. So this is the symplectic side, and the gauge theory side. For any element of homology of your three manifold, you get a homomorphism from the frame floor homology of Y to the frame floor homology of Y, which I'm going to also denote it by mu of alpha again. And these are some variations of Donaldson invariants. So Donaldson invariants are basically polynomials and the homology of your four manifold. Once you pick some element of homology of your four manifold, you can get a four manifold invariant in the case of closed four manifolds. By variation of Donaldson's construction, in the case that your four manifold is Y times R, you get this homomorphisms. And in the case, so remember that, maybe when we look at symplectic instanton homology, we already fixed some Heegaard splitting. So in particular, you can look at elements which are coming from, sigma g coming from this Heegaard splitting. And the theorem that, we have here is that this isomorphism phi from frame floor homology to symplectic frame floor homology is compatible with the action of the quantum homology on this side. In fact, to be more precise, for any element of sigma g, you have mu of alpha acting on symplectic instanton and the I sharp of Y, and that action commutes with the action of phi. It has, this can be a little bit expanded, say something about close open string map, but I should skip it here for the sake of time. There's a generalization of theorem which basically can be proved using similar argument. So let's say that you have now 2-3 manifolds Mi. Now we assume that the boundaries are disconnected, union of sigma g and sigma h. And we also assume that there's a path going from one boundary component to the other boundary component. Remember that once you have this, you can get some Lagrangians inside the character variety of sigma g times the character variety of sigma h. But on the topological side, what you can do is that you can just flip one of these two guys and glue them along their common boundaries. And this variation, the generalization of the theorem that I mentioned before says that if you take the Lagrangian floor homology of these two Lagrangians as Lagrangians inside chi of sigma g times chi of sigma h, then it's gonna be isomorphic to the floor and some version of instanton floor homology, which is associated to these three manifolds, connected sum of M1 and M2 along their common boundaries, with some choice of H2 class, which is coming from this. As a special case of this, you can take your three manifolds to be just a product of some interval times sigma g. And you have some degree of freedom. So what you can do is that, it's correct that the boundary is the union of two copies of sigma g, but what we can do is that we can change the identification of the boundary components using some map, some diffeomorphism of sigma g. So for example, here, I changed the identification of the boundary component of 1 times sigma g of the second three manifold M2 using some diffeomorphism of sigma g. So the effect that this has is that, you know, once you take the, you glue these two guys using this recipe here, the result would be a mapping, the mapping torus of this phi. So you get 0, 1 times sigma g, where you identify some 0.1 in x in sigma with 0 and phi of x. So in this case, the Lagrangian that you would associate to the first three manifold is just the diagonal. And to the second one, you associate the graph of phi star, where phi star is a map induced by phi at the level of character varieties. And this essentially recovers some theorem of Dostagel and Solomon that instanton Floer homology of this mapping torus is isomorphic to the Lagrangian Floer homology of the diagonal and the graph of phi star. I mean, I said essentially because, you know, you want to identify the this Lagrangian Floer homology on the right-hand side with the symplectic homology of your map phi star. And I think this is one of the folklore theorems in symplectic geometry, which I don't know if, I don't think it's, the proof is written anywhere. Okay, I should say that this, okay, so the theorem that I mentioned here, again, expectation is that there should be some generalization for the inverse case, but things would be complicated because you have to add some bounding coefficients and you probably should use some virtual techniques there. So I'm not gonna say much more than this part. Okay, so I'm just gonna maybe very quickly, I'm gonna give a very biased review of three manifold Floer homologies here. So, and using Yang-Mills theory, on the gauge theory side, you have invariants like frame Floer homology, but also some other invariants which are called, you know, the general name for them are instanton Floer homology theories. So this is on the gauge theory side. On the symplectic side, you have this symplectic instant frame Floer homology. Again, this other invariants here should have some counterpart here. I should say that there are a lot of invariants either on both sides, gauge theory and symplectic geometries are not even defined. There's some other theory which would give us three manifold invariants, which is called Seiberg-Witten theory. On the gauge theory side, the invariant, which is much more well defined, much more developed and defined, and in the case of Yang-Mills theory is monopole Floer homology. Similarly, on the symplectic side, we have Heegaard Floer homology. So the Atiyah-Floer conjecture in general is some relation between this column and Yang-Mills theory and the symplectic side, which this, you know, for one of the invariants on the gauge theory side and the symplectic side, we claim that they are isomorphic to each other. But there are much more other, you know, invariants here, and some of them are, you know, for some you can extend, you know, part of this story to some of the invariants there, but the full generality of Atiyah-Floer conjecture is wide open, partly because the invariants are not even defined. But here the story is much cleaner that and this, in the Seiberg-Witten side, the invariants on both columns are defined, and there's an isomorphism between them, which is due to Kutlan, Ghiggini, and Cliff Taubes. I should say that the invariants in the first column are supposed to be more natural, although they are isomorphic to each other, but each column has an advantage to the other one. So the first column, the invariants in the first column are more natural. Like, for example, you didn't have to fix some Heegaard splitting to define invariants in the first column, but that's something that you have to do for the invariants in the second column. But the invariants in the second column are more computable, partly because the PDE that you have to solve here is the Cauchy-Riemann equation, and here it's a PDE defined on a four manifold. Maybe I'd like to say a few words about comparing the two rows. So in general, I guess there are some expectations that the invariance in the, there are some relations between the invariance in the first and the second rows. And it's in the same spirit as Witten conjecture, which says that Donaldson is equal to Seiberg-Witten on closed-form manifolds. But I don't think, everything in the first column, and I don't think they are supposed to be equivalent invariants. There are some pieces of information which are missing on, one invariant has and the other one doesn't have. So for example, the invariants in the first row are more topological. So some manifestation of this is that, like, for example, we had this Chern-Simons filtration for frame floor homology and symplectic frame floor homology. Another manifestation, probably a better one, is that there's a direct relation between the generators of floor chain complexes for the invariance in the first row and the fundamental group of your three manifold, as opposed to invariance in the second row where you don't have such direct relationship to topology. But the invariants in the second row are easier to work with, like they can be defined in an easier way, and there are, there's much more known about the computation of this invariant. So for example, there are like some open questions about, computing some simple invariance for some simple, some analog of, for example, Atiyah-Floer homology here, which is gonna give the proof, some gauge theoretical proof of four-color theorem, just to give some instance of like what the main challenges on the first row is. But maybe, because on the symplectic side, we have many more, the computational tools, maybe, one can use symplectic geometry to, to resolve that issue at least partially, maybe, develop some computational tool using symplectic instanton homology and then pass it using Atiyah-Floer conjecture to the gauge theory side. So that's one of the, motivations maybe for proving, such theorems. I have, I think, 3 or 4 minutes, so maybe I'll just talk about some something which is already known on the symplectic side very quickly, and say that it could have some topological, some implications for this invariant frame floor homology. I'll be very quick, partly because these are work which are very much in progress. I'm not gonna state any theorem or something. I'm mainly gonna talk about some, I'm gonna give very quick exposition of some work of Ivan and Smith here. So remember that the first interesting character variety is chi of sigma 2. And from now on, let's work with complex coefficient. Remember that it's a complete 2-2 intersection. And in this case, you can look at the quantum multiplication by the first chain class as a map from quantum cohomology. And it has 3 eigenvalues, -2, 0, and 2. And I mean, it's well known that once you have this, we are in the monotone setup and we would get some decomposition of our Fukaya category into 3 summands. We would have 1 summand for each of these eigenvalues. So you have eigenvalues in plus or minus 2 summand, and then you have the summand of Fukaya category for eigenvalues here. And this one is supposed to be the most interesting factor here. We already talked about some Lagrangians here, so let me just quickly review some of those. For example, if you have a 3-manifold with a torus boundary, there was this construction, which is boundary sum with I times T2, which would give us some Lagrangian inside this space. We can also, another way of constructing Lagrangians, which is very similar, is that we can get 3 manifolds with boundary sigma 2 and T2 by fixing some closed loop gamma inside our surface and glue a 2 handle to this guy, and then look at the associated Lagrangian here. I'm gonna give some description of sigma. Gonna use some specific description of the genus 2 surface here because I want to introduce 5 curves here. So just think about the genus 2 surface as the branch double cover of the complex plane along this 6 points. Of course, this is going to be sigma 2, and we can take also these 5 arcs and look at the branch double covers of these arcs inside sigma 2, and that would give us 5 loops inside the genus 2 surface. So there's a theorem of Wehrheim and Smith which says that the Fukaya category of the most interesting summand of the Fukaya category of this character variety, at least after when you look at twisted complexes and then take the split closure, is generated by these 5 Lagrangians. The 5 Lagrangians which are associated to these 5 loops. Remember that from the last slide, given any loop, you can get a Lagrangian. And another, not just that, Ivan also can characterize what the infinity algebra associated to these guys are. And so, okay, so I'm running over time. Let me skip this, but I should say that this, very quickly, what he does is that he gets some sort of identification of the Fukaya category of the character variety with the Fukaya category of the surface itself. So it's if you like, this is some instance of the Hansen equal Sabek Witten, and then using a theorem of Seidel, you can get a characterization of infinite algebra. So the idea is that now, once you have a good understanding of this Fukaya category, you might be able to use this to pass the information into sigma 2, which using the work of Seidel, you can get some, you have Seidel and maybe some, also there are many subsequent works on the case of surfaces, that Fukaya category of surfaces, that you can get a good understanding. This is a rather simple, relatively simple problem to do, Lagrangian Floer homology here. So one might hope that such results would be useful to do some computations, at least in a case that you have a 3-manifold which decomposes along a torus. Because I'm running out of time, maybe I'll stop here, and if there's some interest, I can talk more about this part in the discussion part after the talk. But the point here is that this is just a speculative idea that maybe you can use such isomorphisms together with this version of Atiyah-Floer conjecture to pass the techniques from symplectic side to do some computations on the gauge series. Okay, sorry again for running over time. I'm gonna stop.
Okay, let's give Ali a hand. Okay. Are there any questions for Ali? So maybe I'll start with one. I wanted to ask about something from near the beginning of the talk about how you have this Lagrangian chi of m inside of chi of sigma g. And I was just wondering, you had this result about what you can say when that's embedded. Is it typically the case that it's embedded or immersed or what?
There are some examples that you can show that this is embedded, like for example, if you have, so even more generally, I guess let's look at the case that this is a 3-manifold with boundaries sigma g and sigma h. If so you have a map from pi1 of any of the boundary components, let's say for example sigma g, into pi1 of m. So if this map is surjective, then this implies that you can perturb this guy into an embedded Lagrangian. But in general, there are definitely some examples that you can get immersed cases. Like for example, what you can do is that you can just start from your, your example, even from some example which is embedded, and take the connected sum of this guy with some three manifold with some interesting fundamental group. Like for example, Poincare homologies. Yeah, I think even Poincare homologies would be enough. Then I think you would get some immersed examples like this.
Thanks. Okay, let's see. Paolo has a question. Go ahead and unmute yourself, Paolo.
Yes, I wanted to, can your strategy be used also to reprove that monopole Floer homology is isomorphic to Heegaard-Floer homology, or there are some difficulties, and if there are, what they are?
There is still a hope. I think maybe, yeah, it's not completely hopeless, but let me just point out one thing, which is it was important here and it's missing in monopole Floer homology. So here, maybe I should point to some of the slides that I have. So here what we have is that we have this relation between the chain complexes and the nodes. Like, you can identify the chain groups. I mean, your Floer homology groups are the chain groups of your Floer homology might not be isomorphic, but the chain complexes might not be isomorphic, but the chain groups are isomorphic. And this is already used in the proof here. I think, it still, it doesn't say that this is completely hopeless, the approach here, but that would make things more complicated. The other, yeah, I mean, there's one more, never mind. So I was going to say that also maybe even, I mean, even the, when you look at Heegaard-Floer homology, it's not exactly what you would do from Atiyah-Floer approach. If you would start with monopole Floer homology and you want to use the Atiyah-Floer philosophy to get what is the invariant, what is the right invariant on the symplectic side, it's Heegaard-Floer homology doesn't come very naturally. Maybe once you take a stabilization, take connected sum with S1 times S2, which I think is something which is already used in the Kutlu-Handley and Taubes, then things would become a little bit better. But in any case, once you also do that a step and try to compare the theories, there is still one more analytical step that I'm not sure how hard it is to, if you want to apply the same strategy as here. Just, you want to get some identification between chain complexes, which is not correct for any choice of the metric, but maybe, you want to, by some limiting, by looking at some limiting situation, you want to identify the chain groups.
Well, there might be a way around that, however.
Yeah, I mean,
you can define a map between the two that commutes with the surge excess sequences, then you can go inductively.
Say that again.
I think, I'm not 100% sure, but I got convinced at some point that if you could define a map, I mean, let's say a natural transformation between the monopole and Heegaard-Floer functors. So something also that commutes with cobordism maps.
Right.
Then I think you can run inductively the excess sequences and.
I see what you're saying, but Right. Even in the definition of that functor, which is natural, which you want it to be natural with respect to cobordism maps, I mean, you have this matching condition here for on this instanton side. It's going to be a little bit more complicated for Seibert within a story. So I think there is still a hope there, but I'm not sure. I haven't thought, how, try to do that, and I don't know how complicated it is.
Okay, thank you.
Even the definition of this map phi could be a little bit more subtle on the Seibert within side.
Okay, thank you.
No problem.
Rohil, you can go ahead and ask your question.
Oh yeah, sure, thanks. So regarding the four-color theorem thing that you mentioned, I was just wondering if there's any sensible proposed definition of the symplectic side for Kronheimer and Mrowka's web instanton homology that they use for this. Like, right. I guess like you would have to figure out where to position the Heegaard surface with respect to the web and so on. And right. I guess I don't even understand these basic questions, so I was just curious what your thoughts were on this.
No, that's a good question. Yeah, so what you want is that, I mean, like if, for example, if you have a web, let's say in S3, then you want to decompose. So, I mean, one approach to do this is to try to decompose S3 to the union of the simplest, Heegaard splitting, so it's a union of two three-dimensional bar. Mm-hmm. And but then so your web would intersect. I mean, it would intersect, of course, the boundary. So this is not even a web. This is not a good picture. Okay. Maybe you have something like this, and so here the correct symplectic manifold. I mean, one approach for defining the symplectic manifold is going to be the character variety of S2, which is punctured a bunch of times. I mean, there's the analog of the condition that we use, which is you want to use the odd character variety as opposed to even character variety. Here is that you have an odd number of punctures and your S2, and then gamma. You would look at webs with boundary. I mean, webs with boundaries on those punctures. I mean, something which is important in the four-color theorem is that you want one thing which plays a very special role. I guess one family of webs which would play a very special role are planar webs.
Right, and I was thinking something similar.
Yeah, for planar webs, something which is nice about planar webs is that you can pick the Heegaard splitting so that this, your gamma also decomposes along a bunch of points. And in the case of planar, you can assume that gamma I is a trivalent tree. So it doesn't have any cycle. I don't know, I mean, it might. I think if you do this probably would imply that your Lagrangians are Lagrangian tori inside this space. I don't have any, useful idea. I'm just trying to explain what some construction that you can apply to planar webs without claiming that it might not work, of course,
Yeah, got it. Thank you very much.
In the case of planar webs, there is this nice decomposition that might be useful, especially because the output would be a Lagrangian, or associated with planar a trivalent tree, you would get I think a Lagrangian torus.
Okay, thank you.
No problem.
Okay, so so let's wrap up the official Q&A now, and let's give Ali one more hand.